In this video, I want to solve the problem of finding patterns of growth of length exactly n in a list. So here is the statement of the problem. We need to return true if at any point in the list temps there is a sequence of n increasing temperatures, and we need to return false otherwise. So what's an example of this kind of thing? Well, here's one example. So we'd want to say if the list is something like 4, 3, so there is a fall now, but let's say that now the temperatures are rising. So let's say that this is 10, this is 20, and this is, let's say, 30, and now this is a 10 and a 20 again. Well, if you also give it the length of the sequence, 3, 10, 20, 30, so that's 4. In this case, there is a period of 4 temperatures which are all growing. In this case, we should return true. Let's say that we have the same list, but we want a sublist of 5 temperatures that are growing. Well, there isn't one. The longest period of growth here is of length 4, so that would be false. Another example, the same list, but we want a period of growth of length 2. Is there any such thing? Well, yes. For example, here you start with 10, 20. And this is a period of growth of exactly 2. So in this case, you want to say true. Let's try to come up with an example where we should return false because there is too much growth. So here's a simple example. You could say 1, 2, 3, 4, and we want a period of growth of 2. Well, this is false because while here's 2 adjacent elements and there is growth here, but you could continue on and look at the 3. So this is not a period of growth of length exactly 2. So this should return false. And that's why here we say that this example should return false. So in order to solve this problem, I want to first solve a simpler problem. A lot of the time what you want to do is you want to decompose the problem that you're solving into simpler problems. And what I want to do is I want to go back to what we did here with match at, which we eventually used in order to find patterns in DNA at arbitrary locations. So what I want to do is I want to solve a simpler problem than this. And this is the problem that I want to solve. Let me call the function consistent growth n at I, and here you'll have temps, and you'll take n, and you'll take I. So I don't want to look at just exact n. I want to say consistent growth n, and I want to say consistent growth n at I. So basically what I'm asking is, are there n elements starting at index I which are all increasing? So let's define this. So we take in a list and an int and an int, and we return a boolean. And what we want to do is we want to return true if starting at index I there are n increasing elements in the list temps. Okay, let's write some examples. In fact, we could just copy the examples from over here. So let's look here. So here, let's try to supply an index. So if we start with an index of 0, well, this is not true because those 4 elements, they're not in increasing order. So this should be false. let's try a similar example, but in this case, we'll supply the right index. So here you would have index 1, here for example, and this would work. So you have 1, 2, 3, 4, so this works. So this means that this is true. If n is smaller than 4, that would work as well, because we are no longer insisting on having a period of growth of exactly 3 elements. So here you have 3 elements, they're growing. Just because here you have a 30 doesn't mean that you should not return true. Let's come up with an example where we ought to return false. Well, for example, if there is no growth at all, like 4, 3, 1, doesn't matter where you start. Let's say a period of growth of 2, and let's say that you start at 0, and there isn't any growth at all. So let's finish the docstring and say what our arguments are. Temps is going to be a list of numbers, n is going to be an integer, and I is going to be an integer. So okay, let's now write this function. This should be easy at this point. What should we do? We should say, okay, let's look at this example. So here you have 4, and we start at index 0. So what we should do is we should go element by element and check. Is there an increase here? Well, in this case, there is not. If there were, we would check for an increase here and for an increase here. Here we are returning true. We are starting at index 1. So we'll start at index 1. We'll check for this increase. Then we'll check that there is an increase here as well. And we'll check that there is an increase here as well. We have 4 elements in total, so we'd be done. We haven't found a decrease, so we just return false. True. Let us now actually write this function. So what I want to do again is I want to start at index I, so I is taken, and I want to check for an increase so that in total I'll have n minus 1 increases, right? Because I want n elements in total. So for example, if I'm looking here at 4 elements, I'll have 1 increase from 3 to 10, 1 increase from 10 to 20, and 1 increase from 20 to 30. So that was 3 increases. You can look at the spaces here between the numbers because you have 4 numbers, 3 increases. Okay, so here's what we'll do. We are currently at index I. And what do we want to check? We want to check that temps at I is smaller than temps at I plus 1. And we want to check that temps at I plus 1 is smaller than temps at I plus 2. And we want to check that temps at I plus 2 is smaller than temps at I plus 3. How far do we want to go? Well, we want to go until the nth element in this sequence. What's the nth element here? It's usually convenient to say I plus 0 here instead of just I, and then it becomes clear that the last element here should be temps at I plus n minus 1, because in order to have n elements, you would go from 0 to 1 to 2 and so on up to n minus 1. And this last element, it should be compared to temps at I plus n minus 2, like so. Great. How can we set this up? Well, here we have an index that goes from 0 to 1 to 2 and so on up to n minus 2. Let's set up just such a variable. So I is already being used, so we'll use j instead. we want j to go from 0 and up to n minus 2. That means that we need to say for j in range n minus 1. That will make j go from 0 and up to this number, minus 1. Exactly n minus 2. Now we want to make all of those comparisons. So how do we make them? We want to say if temps at I plus j is greater or equal than temps at I plus j plus 1, so the j here would be this j here, and this would be j plus 1. This is j, and this is j plus 1. And we want to invert this, because if it's not the case that this is true, then we know that there is no increasing sequence there, and we need to just return false straight away. If we went through all of those comparisons and haven't returned false, then we get to return true. Notice the analogy between consistent growth n at I and match at. Here, what we're looking for is a pattern of n increasing numbers. Here, we're looking for the specific pattern subsequence. It's basically the same algorithm. I now want to use the same idea that we used with extending match at to simply matching, to use this function in order to find consistent growth of exactly n numbers. How should I do that? Well, here is the strategy. For every possible starting point, I'll try to see if there is an exact growth of n numbers. So here, for example, there are 4 numbers which are growing. Now I'll be able to detect that using my consistent growth n at I. Then I'll also have to check on either side of the growing sequence that things are not ruined because there was actually growth that started earlier, and things are not ruined because the growth is actually continuing over here. First, let's set up trying to check for growth at every I. I'll simply say for I in range the length of temps. So I'll try to find growth at every possible starting point inside temps. So I'll try to see if this works for me, and then I'll try to see if this works for me, and then I'll try to see that this works for me, and so on. Clearly here there aren't even 4 numbers to check, but we'll take care of it later. For now, I say for I in range length of temps, and now I want to check whether there is growth of n elements at all, because if there isn't, there is no point in checking for anything further. So I will say if consistent growth n at I temps n I. So I repeatedly use the same temps and the same n, but the I is changing. Now, if I'm inside this if statement, that means that there is consistent growth at that point. It doesn't mean that there is consistent growth of exactly n, but it means that there is consistent growth. For example, if I were to try to call this function using n equals 3 at I equals 1, I would be inside the if statement. But remember, if I say n equals 3, I will try to check whether there is still continuation here, and I will see that there is. So I got to check. Here is the easiest way to check that there is not consistent growth to the right of the sequence. so to check that this is not increasing further. Actually, in this case, from the 20, we're increasing to the 30. We'll simply use the same function again. Except we'll use n plus 1 instead of n as an argument. Let's call the result of this computation bounded right. What is bounded right? Well, bounded right would be true if the growth is bounded on the right, and it's going to be false otherwise. You want to compute another variable, which would be bounded left. How can we compute bounded left? We can almost get away with using the same trick and saying consistent growth n at I temps. Now here this is still n plus 1, but this is going to be I minus 1. Almost, because there is a problem here. Suppose that I minus 1 is equal to minus 1. That would happen when I is equal to 0, and in this case, this doesn't really make sense. Let's take care of this case separately. We'd say that if I is equal to 0, then bounded left is surely true. Otherwise, we are not sure, and we'll try to compute it as before. We should now go back to worrying about what happens when we try to call consistent growth n at I when there is not enough elements in temps to try and see if there is growth of size n. Let's go back to consistent growth n at I. As you can see, we have not taken care of that problem. Luckily, we already took care of that problem earlier in match at. We can just copy that solution to consistent growth n at I. Let's do that. So over there we said if I plus the length of the subsequence minus 1 is greater or equal than the length of subsequence, then we need to return false. Over here it's the same thing. So what's the largest element that we ever will try to look at? It's going to be I plus j plus 1, where j is equal to this number, n minus 1, minus 1 again. So the largest element is going to be I plus n minus 1 minus 1 plus 1, or just I plus n minus 1. And we want to make sure that this index is still inside the list temps. So we want to say that if it's not, so if I plus n minus 1 is greater or equal than the length of temps, if it's smaller than the length of temps, we are fine, but if it's larger, then this index will be invalid. Then we need to return false. Now that's taken care of, let's actually try and add an example where this would happen. So let's say that we have the list 4, 3, 1, and we give it n equals 3 and I equals 1. In this case, we'd be trying to check whether a sequence of length 3 is increasing over here. Well, there is no sequence of length 3, so we ought to return false. We have now computed both bounded right and bounded left, and so we get to actually return the answer. the answer would be, and remember here we first checked whether there was growth of length n at all, and then we computed variables, the variables bounded right and bounded left. Bounded right says the growth of length n, which we already found, is bounded from the right. Bounded left says the growth which we already found of length n is bounded from the left. So if both of those are true, meaning if bounded right and bounded left, then we ought to return true. If not, we just keep looking. If we haven't found a pattern of n elements that are growing consistently, despite the fact that we looked at all the starting indices, then we ought to return false. I made a little mistake here. Hopefully you caught it. Here I said bounded right is equal to consistent growth n at I, going n plus 1 to I. Of course, if there is consistent growth of length n plus 1 starting at I, that precisely means that the growth is not bounded. That means that I need to invert this. Similarly here, I should say not consistent growth n at I. Let me now check that things work. I copied this example from here, and I want to read in everything. And now I want to execute this line, pressing Alt-Enter. Okay, this returned true. Let me now try this example. So let me just copy everything. And let me try to run this line. This returned false. Let me now try the exact same thing, except with 2. This returns true. Should return true because, for example, here is a sequence of 2 elements which are growing. Let me try this example. Let me copy it like that. And let me try this. This will be